Part A of this problem asks us to figure out the correct orientation for the battery. We can work that out knowing that the magnetic force on the bar must be directed up so that it supports the weight of the hanging mass. If we have the battery orientation backwards, the force would be down and the mass would fall. The upward magnetic force equals the current I times the cross product of the length vector into the magnetic field. If we let the length vector L be directed to the right across the bar, with the magnetic field directed into the screen, the cross product of L into B gives us the correct direction for the force. It's directed up. So we know that the length vector L points to the right through the bar, which means that the current will have this orientation, and it goes from the positive to the negative side of the battery. So we see that point A must be the positive side if the bar is to support the weight. Part B asks us to find the mass m that can be supported given the battery's voltage. We can start by drawing a free body diagram of the bar. There are two forces acting on it, the weight of the hanging mass and the magnetic force with a magnitude of ILB. For the mass to be held in equilibrium, the forces on it must sum to 0. After a line of algebra, we arrive at this expression for the mass. It equals the current I times the bar's length times the magnetic field magnitude divided by G. We can use Ohm's law to replace the current I in this expression with the battery voltage V divided by the resistance. That gives us this final expression that we can substitute all the known values into. We have the battery voltage times the bar's length times the magnetic field magnitude divided by G, and the resistance of 5 ohms. And that gives us a mass of 3.21 kilograms.